be hearing about LWE with quantum amplitude, algorithm harness, and oblivious sampling. And we have two speakers. Han and Yaxin will give the talk.
Okay, thank you. Thank you for the introduction. And as the title shows, our work is a combination of three independent works. One is about algorithm, and one is about harness, and one is about applications to oblivious sampling. So as we all know, lattice problems are conjectured to be hard against quantum computers, but their evidence is not that strong compared to the conjecture that lattice problems are hard against classical computers. So we are asking that question, are lattice problems really hard for quantum computers? And this is our motivation of this work. So our talk will divide into three parts. One is intro to learning with errors and its quantum variant, SLWE. And the second and third is SLWE with specific amplitudes, harness and algorithm, and application to oblivious sampling. So what is learning with error? Here S is a secret vector, and we are given an oracle OS. It will return a random linear combination of the secrets plus a small amount of error. Yeah, look at this example, like the coefficients are known and they are sampled from uniform distribution, and the approximate means that there are a small number of error. The goal of LWE is to find the secret vector given the coefficients and the answers. And here the formal definition of learning with errors is shown as this picture. Here S is also the secret vector, and we use the inner product of S and the coefficient A to denote the linear combination. And here E is the error. It will be sampled from some typical error distribution like Gaussian distribution and bounded uniform. The goal is also to find the secret vector. And here are some typical parameters. And LWE is conjectured to be quantumly hard because if you quantumly solve LWE problem, you will quantumly solve some lattice problems like approximate SIVP, SIS, EDCP like that. And here we show the some reductions in previous literature, including like approximate SVP, SIS, learning with errors, and dihedral coset problems. Okay, so let's back to our motivation, how to use quantum to solve LWE. Actually, we didn't know how to do it completely, but we can first to make LWE quantum. So we introduce the solve LWE problem. Let us recall the formal definition of learning with errors. And the solve learning with errors, the problem is similar to classical LWE. Here S is the secret vector. But in SLWE problem, we are given quantum samples of this form. Here A is the coefficient, and Y is the superposition of some classical LWE samples. F is the error amplitude. Here you can imagine that when you measure this state, this Y state, you can get a classical LWE sample with probability the magnitude of F and square. And our goal is similar to LWE, is to find the secret vector. Here, this definition is dated back to CLZ 2022. Yeah, here are some typically used error distributions, like Gaussian, which is our work is focused on Gaussian, and Laplacian bounded uniform, etc. And here DFT means discrete Fourier transform of our error amplitude. Okay, let's go to the second part. It is SLWE for Gaussian amplitudes, our harness result, and our algorithm. So recall this reduction picture. There is a problem that does BKSW18 work for SLWE? The problem is their reduction only reduces extrapolated dihedral coset problem to the classical LWE problem. And we overcome this problem by showing a reduction from LWE to SLWE with some particular Gaussian amplitude. And our reduction begins by preparing this state. In the third register, we use Gaussian ball to bound the error. But in BKSW18, they uses uniform distribution over a bounded sphere. And then we add the classical LWE instance into this state and measure the third state. The third register, we will get an EDCP state with an unknown center C. Here in our work, the success probability is overwhelming, while in BKSW18, it is 1 minus inverse polynomial. This is the benefit of our reduction. And in step 2, we will do QFT and measure, and then QFT to get an SWE state with an unknown phase. Here, the unknown phase is from the unknown center in the EDCP state. And here is our reduction. Here is the brief introduction of our reduction. And we also show another reduction from LWE to SLWE with unknown phase. It is a quantizing version of RegF05. So you may ask, what is the unknown phase stands for? And we didn't know how to avoid the unknown phase, but we know that the unknown phase turns out to be crucial because we have subexponential timing for SLWE when the phase is completely norm. And this result is a more generalized result because we have this algorithm when the DFT of F has more than one non-negligible point, including Gaussian and Gaussian with known phase. Our idea is first we will apply QFT on the SLW samples and then apply quantum rejection sampling to get a DCP-like states. And then we will use Kuiperberg sieve on these DCP-like states to recover S from these states. We need totally exponential of square root of n log q many samples and the same time complexity. Okay, that's all for my part.
Thanks, Han, for the presentation. In the rest of the talk, I will be showing you our efficient SLW algorithm. It works for a specific amplitude, and it has application to oblivious sampling. So recall the definition of SLWE, that the algorithm gets samples of the form like a state like this. And our work shows that there is a polynomial time algorithm that solves SLWE using only a quasi-linear number of samples. But it works for a specific amplitude f that looks like this. On the point E, the amplitude Fe is going to be a product of a Gaussian PDF and a unit length complex number. And the unit length complex number denotes some Gaussian rotation that is defined by a carefully chosen number P that we'll see in a second. Next, I'll give an overview of our efficient algorithm for this SLW problem with a specific amplitude. So our algorithm receives states like this, and one can view the state Yj to be a box around its center as inner product with Aj. And our plan is going to be, we extract the center of each state Yj, which is S inner product with AJ mod Q, and then solve S mod Q by Gaussian elimination. So this plan won't work usually for amplitude like real valued f. However, with our carefully chosen Gaussian rotation, we have the following key observation, that if you define the set of states psi c to be the boxes around center C, under the condition that Q is far larger than P, the set of states psi c is going to be almost orthogonal. What this means is that you can hope to measure the center of Yj in some approximate basis that extends the set of psi c to extract S inner product with AJ mod P with high probability. It seems like at this point, this already concludes our algorithm. However, there's a major caveat that the above only works for Q far larger than P. In other words, what we want is the center mod Q, but now we can only extract the center mod P. We resolve this issue by restricting the modulus Q to a composite number that factors into P1 up to PL and extract the center under different modulus respectively. And after that, we reconstruct S mod Q by Chinese remainder theorem. We also emphasize that this restriction on the modulus is not crucial because we can always apply modulus switching technique in the previous literature to switch from Q to any modulus Q prime that's smaller than it. In the end, I'll show that our efficient SLW algorithm can be applied to get an oblivious oblivious LW sampler. Very informally, an oblivious LW sampler samples a pair of classical outputs, A, S, A plus E, without knowing the secret S. We don't know any efficient classical oblivious LW sampler, but last year a work showed that there exists efficient quantum oblivious LW sampler. And their idea is to first construct an efficient SLW algorithm and reduces it and transforms it to an oblivious LW sampler. To do this, one first prepare a tensor state where the first register represents the secret, and the second register represents the error with some appropriate amplitude. And then one apply this unitary and apply the SLW algorithm on the second register to solve the secret S from the second register and subtract S from the first register to get the following state. After that, one measure the second register to get a classical sample SA plus E. And since the state does not know a specific S, this oblivious sampling works. And it gives an LW sample with an error distribution that is proportional to the square root of magnitude of F. And specifically, the error distribution does not care about the imaginary rotation in the F amplitude. So we can choose the complex number rather with free will. We improve the SLW algorithm compared to the previous work, and in turn give an improved oblivious LW sampler that is improving the sample complexity. Compared to the previous work, the sample complexity is quasi-linear in the product of dimension n times the Gaussian width of LW error distribution, and we get rid of the dependence on the Gaussian width. So to sum up, we give 2 feasibility results and 1 hardness result. We showed a sub-exponential time SLW algorithm for a very wide range of error distributions that involves almost all the relevant error distribution we know. And we'd like to mention a work presented yesterday in the quantum session that gives a faster quasi-polynomial time algorithm when the modulus Q is a power of 2. We also give a efficient quantum SLW algorithm that improves the previous work on sample complexity. In the end, we also showed that SLWE for some specific Gaussian amplitude with a small unknown phase is going to be as hard as LWE. And that is all. Thanks for listening. We're happy to answer any questions now or during the break.
Okay, thanks for the wonderful talk. We have time for a few questions.
Thank you very much for the talk. Maybe this is a basic question, but the state you mentioned some slides ago that looks like f of e times a quantum register. I guess you need to prepare that kind of yeah, exactly. On the previous slide, the superposition that you had. Yes, the sum of f of ej times something. You need to prepare that kind of state in order to run your algorithm, I guess. Can you give an intuition of how you prepare it?
Thanks for the question. The question is about how to prepare the state.
Yeah.
So for now, for this slide, our algorithm takes input of this state. So the state is going to be given as input, but it's not prepared specifically by the algorithm. And the question of how to prepare this state is a very crucial question, because preparing this kind of state is almost equivalent to be giving an oblivious LW sampler. And what we can show is that if we can solve the algorithm given the state as input, we can also prepare the state on our own. That's some not very tricky reduction, but like basically preparing the state and solving the state are somewhat equivalent.
Okay, thank you.
Any other questions?
So you mentioned about the reduction from LW to EDCP. You improved from the reduction from BKSW paper, and you said like the probability is here like 1 minus 1 over e to the power n. So do we get more samples if we consider the standard parameter of LWE?
Yeah, yes, of course. We can get like any sub-exponential number of samples.
Okay, so in that case, we have like algorithm for EDCP, which is quasi-polynomial.
Yeah, but there are some unknown centers in the EDCP states. So that is the crucial one to avoid us from getting a sub-exponential algorithm for LWE using this reduction.
Oh, okay. So yeah, this EDCP is like there are some unknown like phase also over there.
An unknown center, yeah.
Okay.
In the J register. Yeah.
Okay. Thank you. Makes sense.
Okay, I think we'll move on to the next speaker. Let's thank again for the wonderful talk.
Thank you.